Good morning, everyone. We can start. Um, Today we are looking at the area of receivers in the communication systems. So we are going to look at what type of receivers we can have for both baseband transmission and passband transmission. Just to link up with what we have done so far, just to see where that falls in the communication system. You assume we can begin from the beginning. I think we have done it before, but sometimes it's good to remind ourselves why we are doing all this. So you have your analog signal, and some of the processes which you conduct on the signal. I'm assuming some of them you have done things like sampling, because they are not in our syllabus, so I assume you must have done them in some FE420 something. Yeah. So you do your sampling, and after sampling, of course, you do quantization, and you end up getting your and then you do encoding. You end up getting your codes, your zeros and ones, which are representing, basically they are representing your analog signal. And there are a few things you can do with those zeros and ones. You may decide to do compression. After generating the zeros and ones, you may decide probably, although actually most compression is done before that, but you can also do compression even after even after generating the zeros and ones. But we are going to look in the second semester at compression, which is done before, especially when you're dealing with symbols, with characters. Yeah, not with things like voice or with characters. We are going to see that in second semester. So you have your zeros and ones, and you can either do baseband transmission or a carrier transmission, which you call passband. So the case we are going to look at the matched filter, you look at when you have symbols. Yeah. So those symbols could actually either be from baseband transmission or passband transmission, but we'll concentrate more on where it is actually from baseband transmission. And you remember, I think we did both. The baseband is where we also call it line encoding, is where you are encoding, or rather you're converting the 0 and 1 into some pulse. So we are going to look more at pulse transmission into some pulse. For example, you remember, I hope you can remember, we had the NRZ, we had the RZ, we had the Manchester, we had those different ones. So now those waveforms are the ones we want to be able to identify whether the waveform we are receiving represents a 0 or represents a 1. Yeah. because that's the whole idea. So if you know it represents a 1, then you are going to receive a 1. So you are going now to reproduce the stream of bits which was sent, or rather um, which had produced the pulses at the transmitter. But in the meantime, of course, we know those pulses are not, they have changed shape because they have AWGN, they have additive noise, yeah, and also they also suffered some distortion, yeah. There's intersymbol interference that may have affected the shape. I think you also remember we had, even as you are talking of the pulses, they are not the square pulses, yeah. They are actually least cosine pulses, because if you are doing if you are sending symbols, you know that you can also have intersymbol interference. So to reduce intersymbol interference, actually the pulses we are receiving are actually the least cosine pulses. Yeah. So well, that's the closest we can get. Otherwise, the ideal pulse should be the sync pulse, but we show that the sync pulse would have a problem because it means it goes from negative infinity to infinity. I mean, it's not a practical pulse. That's why we use the least cosine pulse. So I'm sure with that you can now be able to reach where we are. So we have reached at the receiver. So this is a signal we are calling GT. Yeah, this is a transmitted signal. We are assuming what it is going to get us, what is in the channel is the noise. It's going to get noise. Noise is additive. That's why we have this addition here, this summation here. So the output is XT. Yeah. So now we are saying how can we be able to maximize the signal to noise ratio? And we are saying we are going to show that if you have this matched filter, if you have a filter which is related to this waveform, since you know the waveform, yeah, you know the waveform, we are assuming this is a case of where you have a known waveform. For example, it can also be radar. So you know the waveform you have sent, so you know what you're expecting back. But even then, we are trying to, I mean, it's a communication system, so you know what was sent at the other end. Yeah. So we are saying if you can match, if this filter can match the shape of the GT of this signal, the input signal, that is before it is contaminated with the noise, then you can maximize the signal to noise ratio. And now it will be the business of the decoder. Yeah. Because the decoder is the one that does that part of deciding whether it was a 0 or a 1. It will look at the resultant waveforms and it will be able to conclude whether indeed what was sent was a 0 or a 1. So the system looks like this. So that is a XT. XT goes with the match filter, and what we want to find out is what should be the value of this filter. And we are going to find that to maximize that, it will need to be an inverse, a time delayed inverse version of this input signal. Which presumably is a signal which was sent at the other end, because we are saying you can see this is before you get to the channel. So presumably what was sent, but of course what is received has suffered additive noise. After that, of course, we are sampling this, because remember these are pulses, so you need to sample them. You need to sample them at that particular time when you expect the pulse to be a maximum. Yeah, so it means you have to sample them at periods t. I mean, at nt. Let's just put it nt. So you have to have a sampling period of t, where t is actually the period of the input waveform, which is this one. We are calling it input because it is the input to the receiver, yeah, not the input at the transmitter. So NT, of course, is the EWDN noise with the zero mean and variance N0 over 2. We use N0 over 2 because we are talking about the two-sided noise, and when you derive the N0, it assumes a right-sided, one-sided noise spectrum. So that's why we use N0 over 2. N0, of course, is a figure, is just the temperature, the noise temperature multiplied by the Boltzmann constant. That is the N0. So we are going to work. So there is a known figure actually, N0 over 2. But we always put N0 over 2 because that is dependent on temperature. It's not fixed. Boltzmann constant is a constant, but N0 over 2 is not a constant because it will depend on the temperature. Yeah. So that will be the block diagram for symbol detection using matched filters. This is a general case, but of course in most cases you have only two symbols, two different types of symbols, so you only need two of these, and in fact in some cases you only need one of that, because if it is not one, it's the other, so you don't need to detect whether it was a 0. So long as it was not a 1, then it's obviously a 0. So in most cases it will just be something as simple as just one matched filter and not a bank of filters. This one is assuming that this symbol could be many symbols, but in the case of baseband signaling, this is likely to be just one. In the other case, of course, if you are going to use this, if you are going to use the match filter, for example, for because it can also be used with that. If you are using it for passband communication, you could be having many symbols, where those symbols represent multiple bits. I hope everyone now is okay with when we talk about symbol. Symbol is what you transmit to represent the information, to represent the bits. Yeah. So where the baud rate is the same as bit rate, which means every bit is represented with one symbol, then that can only have two levels. Yeah. But in some case, which is the case when it comes to baseband transmission. With the passband, well, you can still have multiple levels in baseband transmission, but it's not encouraged, especially if you are going to use using pulses. Then you are either using an amplitude or a change in amplitude. So if you are using amplitude, you can see why it's not desirable. You don't want to have, maybe I can just explain what I'm trying to say. Because you are going to have multi-level signaling in basebands, that would mean, for example, having 5 volts, then you have another level, and maybe another level. So of course you can have that. So you have this representing 00, 01, 10, 11, or something like that. But you can see, because of additive noise, if this was added some noise, the receiver may detect that as 01, which of course will result in a bit error. And again, we are saying bit error. It's using a symbol error, but that symbol error, of course, will be result in a bit error if you have used the correct encoding, the gray coding. Because the gray coding is from 1 to the closest level, the only difference is 1 bit. Yeah. I hope you can remember that, so we don't have to go into that in details. So in most cases, we are dealing with just not one patch filter if you're dealing with baseband encoding. Because of course, symbol, whenever you talk of symbol, does not mean necessarily a pulse. Symbol is used both with pulses and also with the carrier modulation. So you have your input. Your input, of course, to our system is this, because this is not an input we are putting. This is happening in the channel. Yeah. So our input is this one, x of t, and this our time inversed. Actually, it's supposed to be time inversed, and the conjugate. Actually, it will be a conjugate of this waveform, which is delayed and time inversed. Time inversed because this is gt and this is minus gt, and the conjugate and this delayed by t. Yeah, that's what it means. But of course, for real signals, then it's simply gt minus t, g of t minus t. But we always add this because the signals could be a complex signal. Yeah. Then, of course, we said you sample at t is equal to t, and then after that you have a maximum likelihood decision rule. So there will be a decision rule there. Maybe the rule might be if the signal to noise ratio exceeds this, then that was a 0. But that's what this means. This is a decision stage, and so there will be that rule in the this part is normally called the decoder. Yeah, and this part is called the detector. Yeah. So normally the receiver consists of the detector and then the decoder, a digital receiver. Yeah, so this is the output, which will be one of what was sent at the receiver. Because what you want to know here, what we call the decoder, is not what came in here. It's what was sent at the other end. Yeah. What, in fact, we are going now to whether it was a 0 or a 1. So the output here will be binary, 0 or 1. If this is a digital communication system. Yeah. You notice even for a digital communication system, we are still using this because this pulse is actually an analog signal. Yeah. It's not a discrete signal, but what we are going to produce here is to make a decision whether it was a 0 or a 1. Yeah. So I hope we are together so far. So what we are going to do, we are going to derive, we are going to do this derivation of the match filter, and we are going to use concepts. Hopefully you are familiar with. Some of it is what we just looked at the other day, and others I assume you must have done them in, you must have come across them in either complex analysis. We're going to use the Cauchy-Riemann, not Cauchy-Riemann, Cauchy-Schwarz. Cauchy-Riemann is a different, Schwarz equations, not equations, inequality for integrals. That's what we're going to use to show that this will give you the maximum signal to noise ratio. So the output of the linear filter, of course, has two components. Yeah, there's two components because it has two inputs, this and this. So the output of that, the two are added. So this has two components, and therefore once it goes through here, it also has two components. One due to the noise, and the other one due to the signal. Yeah. As I was saying, the output of the linear filter. So we are talking about at this point, this is the linear filter. Yeah. Would have two components because you have two components. So one will be the one which is which you get, which will be a convolution of GT with the impulse response, and the other one will be the convolution of NT, yeah, the noise with the same impulse response. I hope all of us now are quite familiar with what is impulse response. Yeah, is the response a system gives when is given the sample, the unit sample. Yeah. So signal G naught T, which is the output at this point, what we are calling G naught T, is G of T convolved with H of T, and using the convolution theorem, we know that G naught F is just H of F times G of F. Yeah. So G naught T, you can get will be the negative infinity to infinity, H of F GF E J to the pi ft df. You can simply do the inverse Fourier transform. So we want to deal with the integrals, yeah, because remember we want to use the Cauchy-Schwarz theorem for integrals, inequality for integrals. That's why we are trying to get these integrals. So the signal power is G naught T, of course, is going to be this times this. Yeah, okay. So the signal power, of course, will simply be this squared, the magnitude of this squared. the modulus of this squared. Yeah, that will be the signal power at t is equal to t. That is at the sampling time, sampling moment. It will be equal to that. Yeah, that's the signal power. Note that equation. I had not named the equations. Yeah. So what we want is to get the noise power. Output noise component is given by the convolution of the input noise with the impulse response. So N of t is equal to Nt times h of t, N of t times h of t, which is the impulse response. I mean, not times, convolved with, sorry. The noise is a random process, and for a random process, the output power spectral density for a no-charge system is given by this. Again, we did do this, but actually this one can be derived. You can look in the textbooks, you can see the derivation, but for our case, we will not expect you to derive it. It's a long derivation. It's not an axiom. You can actually derive it. So it means the output power spectral density is simply the input part spectral density multiplied by the modulus of HF squared, yeah, the absolute value squared, yeah. So that is the general equation. So for our case, S N naught F, that's for the output noise. The power spectral density of the output noise will be the input noise S and F times HF multiplied by the modulus squared of HF. Yeah. So I hope we all get this. We are saying that for the noise being, it's good to note that for the noise being what are we? Being a random process, this is how you get the output, the power spectral density is related, the output power spectral density is related to the input power spectral density by this formula. So for the noise, it is that. So note that equation. So the output power of noise is given by the variance, and remember that we have seen that the variance actually is given by the variance, which is actually this, which is actually the same as negative infinity to infinity S naught F df, because it makes sense. It's actually the power spectral density integrated over the entire spectrum, yeah. S naught F, yeah, S naught. I'm saying you don't even have to remember about these variants. The output power is simply this, yeah. Yeah, it is this because this is the power spectral density, which means you are talking about power per hertz. Therefore, you simply integrate across the entire frequency. That's what you're saying. Yeah, that will give you the power. If you're using the power spectral density, if you're using the energy spectral density, then it will give us the energy. But in this case, we are more interested in the power. Yeah, we are more interested in the power because we are trying to find the signal to noise ratio, and by definition, that is the power of the signal divided by the power of the noise. So S naught F, which of course is the same as we know this, is this, yeah, because from here S naught F is this, so we can replace S naught of F with Sn of F, which is squared dF. Yeah, so that is the output power, signal power. No, sorry, noise power. So it means now we actually have both the signal power and the noise power. So this noise power, but also we also know that Sn, this is N naught over 2. Yeah. So actually this is the same as N naught over 2. Yeah. So the signal power is actually this one. N naught over 2 the modulus of Hf squared df, which is not N naught over 2, the integral of the modulus of Hf squared df. So we have these two equations. This noise and where? And this signal. So we have these two. This is a signal power, and this is a noise power. Yeah. So now, of course, we have our signal to noise ratio. So signal to noise ratio at that particular point, at the sampling point, is given by this, by simply the signal power which we got divided by the noise power. And this is what we want to maximize. Yeah, this is what we want to maximize. So we are saying the value of Hf is equal to Hf naught for maximum. Yeah, H O here is meaning the optimum for maximizing. For maximum SMT is calculated using Sibat's inequality. We want to find that optimum. Yeah, H of F. Yeah, using Sibat's inequality, and this is the Sibat's inequality for integrals. Yeah, it's an interesting inequality. We are saying that if you have this relationship here, where f1 of x is a complex conjugate, or whichever is conjugate. Let's say f of 2 of x. Okay, f1 of x is a complex conjugate of f2 of x multiplied by some arbitrary constant. Yeah. Then this inequality holds. This inequality holds if this relationship is true. If this relationship holds, then this inequality holds. Yeah, that's what we are saying. So we are saying f1 of x, the modulus of this integral multiplied by this integral. Yeah, that is the integral of this multiplied by this. That integral, you take the modulus squared. So you multiply the two functions and then integrate with respect to x. And then square, get the modulus and square. It will always be equal or less than getting the modulus of fx, squaring, and then integrating with respect to x, multiply by doing the same for this other function, for the second function. Yeah. So this inequality holds in that. So and of course this term is complex conjugate. I hope it's very clear. meant to be. That's the same for complex conjugate. I think we all know the complex conjugate, especially our complex number. Of course, complex conjugate applies to any binomial expression where you have two variables, but specifically we're doing the complex conjugate of we are doing the complex conjugate. So we are saying x plus jy. A complex conjugate is x minus jy. So let's see. So we can say we want to compare the two, using our equations of interest. So let HF be f1x and GF e to the j2 pi ft be f2x. Yeah. So we are saying, so we have repeated this f12 and this f2 and f2, f1x and f2x with these two, HF and GF e to the power of j2 pi ft. So the integral of HF, h of f, g of f e to the j2 pi ft, capital T, g df squared is equal or less than HF, the integral of modulus of HF squared and the integral of the modulus of GF squared. And of course this only holds when this is a complex conjugate of this. Yeah? That inequality only holds when this is a complex conjugate of this. Yeah. So what do? We divide both sides by, of course, if you look at this equation, you notice this is a signal power. Yeah? You notice this equation is a signal power. I think we have it somewhere. It's a signal power here. So this is a signal power. Where are we? Oh, we passed here. We are here. So if we, where do we divide? I want to say where we say we divide. Oh, okay. We are here. You notice this is a signal power, and what we are doing is we want to divide both sides by this. Of course, when we divide this by this is a noise power. We are saying divide by the noise power, and this side is the signal power. So we are saying what we are going to get is a signal to noise ratio. Yeah. So we are saying if we divide this, so we are going to get this is equal or less than this, because if you divide this by the signal power, what will happen? Yeah, this becomes signal to noise ratio, but this, what happens if you divide this by signal power? Of course, this will cancel out. Yeah, and of course this will become, since this is a this is the denominator. Yeah. So this will become, this is the denominator. This will cancel out, but this will become 2 over n naught, and you are going to remain with this part. You are going to remain with that. So we are saying that this must be equal to or less than this. Yeah. So this must be equal to or less than this. That's what we are saying. Yeah. But we also know that this GF squared here, this one here, this actually is the signal power. This is the signal power, E. Yeah. So actually, no, it's not even signal power. This is GF squared DF. Yeah. Yeah, this will be the signal power here. So which sometimes write it EX. So this becomes 2E over N naught. So we are saying this is equal to this. So the maximum will be 2E over N naught. If you say this inequality is equal to or less than, it means the maximum is actually that, yeah. Where E actually is the energy for the input signal. E is the energy. So to get power, you must divide it with T. So E is the energy for the input signal. So E is equal to that, yeah. And we are saying this inequality holds only if HF, which is equal to H naught F, is equal to GF E to the J pi 2FT. And because this was the Fx1, F1 of X, and this was F2 of X. When we started in a SWAT inequality, that was F1 of X, and this was F2 of X. So we are saying that only holds when this is, so we have gotten, one we have already sorted out. We are saying that the maximum signal to noise ratio only depends on the energy of the signal and is inversely proportional to the power spectral density of the noise. I think that's one of the things we had observed here at the beginning. But the maximum output signal to noise ratio only depends on the energy of the input and is inversely proportional to the PSD of the noise. So we have to determine that. It only depends on that output only depends. It doesn't depend on anything else. It's inversely proportional to the noise and directly proportional to the energy of the signal. Yeah. Now, what you want to find out is the second one, about the time in burst and delayed version. So we have this is equal to this, which is the same as this. You can remove the conjugate from outside and make this is a conjugate, not conjugate. It's conjugate of GF, and so you can actually have this. The conjugate of this is simply the conjugate of this times the conjugate of this. Is as you can see, the linear operation. Yeah. So this becomes conjugate of this, and of course the conjugate of this is e to the minus j 2 pi ft. Yeah. So you just get conjugate and multiply with this. So h of t is simply the integral of h of f e to the j 2 pi ft df, because what you want to get is the h of t. You can get that from the h of f. Yeah. So h of t is equal to this. Yeah. I wish everybody is able to follow. You can try generating it yourself. So from here we can replace which one? Yeah. H of f is equal to this. Yeah. So we can replace h of f. See, H of f, the condition for our inequality, it means h of f is equal to this. So we can actually replace this h of f with this. Yeah. Yeah. So we replace h of f with that, and then multiply with this. Of course, these formulas you are familiar with them. Ideally, they're supposed to have 1 over 2 pi, but that is not important. It's a constant. Yeah. Df, then what is that? So once you do this, you can reorganize this so that you have this. Yeah. So this becomes, well, this is simply the same as this, because this is e to the minus 2 pi ft of t, which is this times, because you are adding the exponents, times e to the minus, and minus of course becomes plus, is df. That's where we are. Then, so this is what we have. Now you can go back and take the conjugate of this. So you can write it like this and then take the conjugate. The operation we had done here before, when we introduced it before here. Here we are saying the conjugate, you can actually just make it a multiplication of the conjugate of the two terms. Yeah. And that's what we are doing here. The other way around. We are simply saying you can put the entire conjugate of this, so it means you conjugate this and conjugate this and put the conjugate outside. Yeah. So if you conjugate this, of course this will become plus, and then you put the conjugate outside. Yeah, conjugate outside. And this, just by definition, because normally what you have is for g of t, you will have this as g of f e to the j 2 pi f t. So this is like the t, yeah. So definitely this, it means this is the same as g of t minus t, and of course in the conjugate. Yeah. This taking the part of the t, this equation. Yeah. And of course for our new volume signal is simply time inversed, and time inversed and delayed by t. For complex signal is simply time inverse delayed conjugate. Yeah. And that is the derivation of the matched filter. I'm sure now you are confident you can be able to derive this. The whole idea of deriving it is not so much the work of deriving it, is that when you can derive it, it means you have understood quite a number of you have quite understood a lot of concepts, because it means you have understood the Fourier transforms, the inverse Fourier transforms. You have understood how to get the output of a signal when you know the impulse response. You get the output when you are given the transfer function, Yeah, you know how to get the output when the signal is random. Yeah, when the signal is random, how do you get the output from the impulse response? And I think that we have seen here. We didn't do the derivation, but it's an interesting derivation. You can get in a textbook, you can go through it, but it's not necessary for us. But sometimes it's good to go through the derivation and to make you understand. It's a lengthy derivation. Yeah. It has also made you understand the Cauchy-Schwarz inequality of integrals. Yeah. Any question about matched filters, the matched filter receiver? So that is the matched filter receiver. We are going to look at, I don't think we'll finish, maybe we can finish in the afternoon, maybe we can finish it, but I think maybe we can finish this remaining part. Then we don't even have to meet in the afternoon. Yeah. What is the feeling of everyone? We try to finish, we do the full hours, then we don't come back in the afternoon. Or we stop there and then look at the other one. Yes?
We try to finish now.
We try to finish now, very good. Yeah, I think it's not a long one, we can finish. Then we don't have to meet in the afternoon. But what is important is that you have understood, because you can finish, then you don't understand, then it's not good. It's only good if you understand. So we are going to look at the coordination receiver. But before you look at that, we look at this thing we call the geometric view of signals. Yeah? Because that's what we are going to use to establish the how the coordination receiver works. So if you have an n-dimensional orthogonal space, you know, of course, sometimes the concept of n-dimensional orthogonal space sometimes doesn't seem to make sense. It's not very intuitive, but because we are normally used to the Cartesian plane, yeah, which has only one dimension, but we also used to the other one, the XYZ. But now we can't imagine beyond XYZ. Yeah, but you can have an n-dimensional orthogonal space. I mean, this space can be defined as, or otherwise, I think my English is wrong. Characterized by a set. I think an n-dimensional space, I think is supposed to be, is characterized. I think is characterized. That's a better term. I think I was trying to think of which word to use. I ended up putting both. By a set of n linearly independent functions pi j of t called the basis functions. What is important about basis functions is that when you integrate them over a period, or rather when you do what you call the dot product, you get 0. And that is very important. I found that when it's a concept now we use in telecommunication, yeah, because if you have two orthogonal signals, you can actually transmit them together Yeah, they interfere with each other. And as the receiver, if you take the dot product of the incoming signal, to make sense, you can know whether which signal it is. I mean, if you have one signal which has a cosine in it, and the other one has a sine in it, you see, it is a maybe AC cos omega ct, and this is AC sin omega ct. If you do the dot product, which is actually the integrating of a period, if you do the dot product of this with, let's say, a cos omega ct, yeah, it will give you some finite value. If you multiply this, if you multiply this and then integrate, which is actually the dot product. I'm saying if you multiply this, then integrate, which is the dot product, it's going to give you some finite value. Yeah, some finite value. I call it x or something. But if you multiply with this and then integrate, which is the dot product by definition, then this will give you 0. Because sin omega ct and cos omega ct are orthogonal. Yeah, and that is a test for orthogonality. Yeah, so you can see this is a very simple mathematical operation, but it is very important in telecommunication. That's why sometimes the basis functions we use with most of our signals is actually the cosine and the sine. Yeah, those are the orthogonal basis functions we use. Yeah. So any arbitrary function can be generated by a linear combination of these basis functions. Yeah. The basis function must satisfy the condition, this condition, that is 0 to t, phi of jt, phi of kt is equal to kj delta j, delta sub k, I should be saying kj, but actually k sub j, delta sub j of k for this period. And we are saying where k and j move from 1 to n. And this function delta sub dk, this actually is called the Kronecker delta. Yeah, is 1 for j is equal to k and is 0 otherwise. Now this one, if you try to look at it like I, j and k means 2 dimensions, of course you get more confused. It's more of a concept which you are going to see how important it is. It's more kind of abstract. And actually it's very similar to the delta we know, which is the other delta, the Dirac delta, except the Dirac delta is one-dimensional. Yeah. So this is very important. So we are saying for j is equal to k is equal to 1 and 0 otherwise. What we are saying is if these are orthogonal, then if you do this operation, it's going to be 0, except when j is equal to k. J is equal to k just means you're multiplying it with itself. It's like multiplying the cosine with a cosine, yeah, and not, because this is, remember, this is we are talking about an orthogonal space. So we are assuming all these are orthogonal. We are assuming these are orthogonal. Yeah. So if they are orthogonal, so long as what you are multiplying here is not the same, that's what it means for j is equal to k is equal to 1. Because this is equal to 1, this is just some value. Yeah. That equation is very, very, very important. Yeah. When I'm trying to explain with cosine, it is easier to understand orthogonality with cosine and sine because it talks about perpendicular. And in most cases, we draw the cosine on the x-axis and the sine on the y-axis. Yeah. As we know them as perpendicular. So it's easy to conceptualize when we talk of the cosine and sine and the orthogonal basis which we normally use. So that, I think the concept will become clear as we go on. So when k, j is equal to 1, that is the basis functions. So if this is equal to 1, this one, you're seeing this one. When this is equal to 1, then it means this is equal to 1 times 1 or 0, one of the two. Yeah? So it is 1 times 1 or it is 1 times 0, depending on whether j is equal to k. Yeah? So this k, j is not referring to this, j is referring to this one, this capital K, j. Yeah? Is equal to 1, that is, we have normalized, then we don't talk about the orthogonal basis functions, we talk about the orthonormal basis functions when you normalize. So it becomes the orthonormal space. Yeah? When the functions are normalized, then the space is no longer known as orthogonal space, it's known as the orthonormal space. So, and the normalized orthogonal basis functions are called orthonormal basis. So, orthogonal basis would be like cosine and sine. Orthonormal basis, of course, will be like the vertical. Yeah. Will be like just this is equal to 1. So this will be orthonormal basis. This is simply 1. This is equal to 1 because they are orthogonal, but then they are normalized. So this will be orthonormal basis. Yeah, and probably also the in the y direction. Yeah, in the z direction like that. Yeah. So let's see the application of this. In the arbitrary finite set of waveforms, SIT, going from I to M, can be expressed as a linear combination of n orthonormal waveforms. That is phi 1 of t, phi 2 of t, up to phi n of t. We are saying this I, each of these can be expressed as orthonormal, as a combination, linear combination of n orthogonal waveforms, where n is less than m. Yeah, the m, this I goes from 1 to m, the n goes from 1 to n. These are the orthonormal bases. These are the finite set of waveforms. Yeah, I think it is easy when you see it that way. It means S1 of t, I is varying from I 1 to m, and the orthogonal basis, yes? Oh, somebody else. Okay. And orthogonal basis has moved from 1 to n. So you can have this to, these are many of them, of course, going from, so it will be S1 of t is equal to A11 phi 1 of t plus A12 phi 2 of t up to A1n by n of t. Yeah, and of course the same with S2 of t is FEE521 by 2 of t. I think this one is going for, no, this is still phi 1 of t. Phi 2 of t. This one it is varying phi 2 of t. So you go up to that way up to Sm of t is Am1 of t by 1 of t plus. So these are the different waveforms represented as a linear combination of this orthogonal basis. Yeah. And of course, this can be written as Si of t is the summation of j is equal to 1 to n. We're simply just writing the same thing here. Yeah. So when we are writing this, we can write that as this for Hij by j of t, where I goes from 1 to m, and j, I mean where I goes from 1 to m, and n must be less than m. Where Aij is this integral. You can get this Aij by simply integrating Sit with phi j of t dt. Yeah. Oh. So now, as a transmitter, we are trying to see how you can recover your signal at the receiver, but you want to see what has happened at the receiver so that you can recover at the transmitter so you can see what will happen at the receiver. So at the transmitters, the signals to be transmitted are multiplied with the basis functions, pi I of t, and summed up. And we know, of course, that's what we do with our receivers. We normally, in most cases, we only be having two of these signals. One representing a 0 and the other one representing a 1. Yeah? And then that signal, you're going to multiply it with our basis functions. And the basis functions we normally use is a cosine and a sine. And then we transmit them together. But this is a general case. But I think you can easily relate with our transmitters. For example, with a passband transmission, we normally get our signal, we get our data, convert it into signal, and then, of course, modulate the carrier, and this phi of t is usually the carrier. Is a cosine waveform, yeah? And then we combine that. You can remember our QPSK, how it looked like, yeah? So we get that, and we get our output SIT. And you can see this SIT is actually a linear combination of this. Phi 1, you have simply is AI1 times phi 1 of t, AI2 times phi 2 of t, up to AIN times phi n of t. Yeah. So this is a linear combination of. So you're saying this signal you're transmitting is actually a linear combination of this, of the signals you want to transmit. You can see how well it works for us. Yeah. So we are saying now this and the receiver, it can be shown that Aij can be recovered at the receiver by multiplying the received signal with the basis functions and integrating over the symbol duration t. Yeah. So that is the basis function. The basis functions, there will be the basis functions is these signals. Yeah. And what you are doing is you're multiplying with the basis functions at the receiver. That's why this equation comes in. Yeah. That when j is not equal to k, you get an output. And if it is equal to k, if it's no, when it's not equal to k, you get 0. When it's equal to k, you get an output. So it's 0 when j is not equal to k. Yeah? Because to mean if j is not equal to k, then you are multiplying two of the well-known functions and then integrating them over t. And that is supposed to give you 0. It will mean they are orthogonal. Yeah? And the only signals you have are actually the cosine and sine. So they are orthogonal. So it's only when you multiply cosine with cosine or multiply sine with sine that you're not going to get 0. Because cosine is not orthogonal to cosine. Cosine is orthogonal to sine. So I hope we are all together. I hope everybody is following. Yeah. So I keep on telling you, when you're online, only you can tell me you are not following. When I'm in class, I have the advantage of just looking at your face and knowing that you're not following. But online, you have to talk. You have to tell me. If I move too fast, tell me. We'll be back. I did not understand that particular concept. Because in reality, that is supposed to be my job, to make it easier for you to understand the concept. Otherwise, you don't even need me. If you don't read this, you can understand the concept. But it will take probably a bit longer. Yeah? But when somebody else talks about it, that's my experience. Yeah? That's how people go to class. So if you don't understand, you can pull me back. But the silence, I'll assume that everything is clear. So you have got that at the receiver, at the transmitter, sorry. Oh, going back. Where is my... Where was I? The figures look so... this is where I'm looking for. This is at the transmitter side. So this happens at the transmitter. So this is what has been transmitted. And in this case, we have taken we are demonstrating this. We are making the assumption that there is no noise. And we are looking at the straightforward case of a noiseless channel. Yeah. So it can be shown that, so you can do that. It can be shown that EIJ can be recovered at the receiver by multiplying the received signal with the basis functions and integrating over the symbol duration t, and that's what we are going to do there. So we know our signal Si of t is simply the summation of we said it's a linear combination of this. So it's simply the summation of j is equal to 1 to n aij phi jt. I goes from 1 to n. This simply saying that our signal is just a linear combination of this scaled because this is a signal. This is what we wanted to send, and we multiply by this. So just scale by this, or we scale by this signal here. So SIT, we are multiplying both sides by phi AT. We are assuming it's on the normal basis, but we are calling it K of T because it's varying from 1 to K. Yeah, that K must actually be the same as a J. But why we use this is because it can be any. K in this case, when you use K, I think it is good to clarify. So we are saying this could just be the basic function. So we are saying one of them is J is equal to I is equal to 2 and K is equal to 3, So we are talking about when we mean by K being not the same, it means I think my explanation is not very. Yeah, what we mean by using the I, J, and K, it just means different values of this. Yeah, does not mean that we have more variables. Yeah, it just means we could be talking of K as 1. Yeah, so that is A1, and J as 2, so that's A2. So if K is equal to J, it means you are multiplying A1 and A1 or A2 and A2. That's what this means. You might confuse it to mean that you're referring to two variables. That subscript could just be the same variable, but with a different subscript. So if you multiply by phi kt, this is what you're going to get. Yeah, at t there. So this is equal to this phi kt. Integrate both sides from 0 to t. Yeah, so integrate both sides from 0 to t. This I should always put this multiply by phi k of t. That's how it's put that dt. So you're going to get that. Yeah, you have integrated this. So you can put this outside the summation of aij. It does not depend on time. So when you integrate with respect to t, you can put this outside, and so this si of t phi k of t dt is equal to this times this, and this will be 0 for, because these are orthogonal basis functions. For j is equal to k, and 1 for j is not equal to k, and 1 for j is equal to k. So this will be aik, because it will be 0 for when they are not when j is not equal to k. Yeah, and 1 for j is equal to k. So we can say this is equal to the aik. And what are we saying here? So we are saying this was a signal that was multiplied with your orthogonal basis functions. And we are able to recover it by simply getting this signal. And of course, this is SIT, so this is varying. So it means for S1T, So this SIT was, of course, S1T plus S2T plus S3T up to SMT. I think that's what we are saying. So those are the different signals. Yeah, yeah, and each of these has got n orthogonal bases. Yeah, but these are a combination. This is the signal you are carrying, which is a combination of these signals, and each of these signals is a linear combination of the orthogonal bases. Yeah. So we are saying we are able to recover. So we are able to recover A, for example, A1K. We are able to recover each of these at the receiver. A1K with S. We are able to by simply integrating, multiplying this with the SIT, the symbol representing it, and then integrating over T. And if you look at it, that's what we call the collidator. You are simply multiplying and then integrating it with respect to T. And that's what we call the collidator. That's the collidator, yeah? Yeah. And what we're doing is actually we're doing what we call the dot product. And so long as what you have received here, you are multiplying with one of the other orthogonal pieces, it will give you 0. So it's only when you multiply with the signal that generated it. Yeah, the product of that signal with the with that particular orthogonal basis. If this orthogonal basis is the same as the orthogonal basis in that particular component, then it's going to give you some output. Otherwise, it will give you 0. If it is any of the other, because they are all orthogonal, we are assuming phi1, phi n are all orthogonal. And of course, when you use the term perpendicular, it becomes a bit counterintuitive, because we know perpendicular just means you have only 2 lines, you have only 2, yeah? So you may not be able to kind of imagine it. Because so far you have learned that orthogonality just means being perpendicular. Orthogonality just means if you multiply the two and integrate it, or rather if you take the dot product, you get 0. So that's how the coefficient receiver works. And I said again, this will depend, you have as many coordinators as the number of different symbols you have representing your different signals. What we are saying here is this SIT would have been, maybe you have 0, 0, 0, 1, 1, 0, 1, 1. So you have one symbol, S1T, S2T, S3T, S4T. These are actually what you're saying is the signal you are carrying, it's just a linear combination of these. Yeah. And we're saying that can happen for any signal. But this happens to be the signal we have created through modulation. And so our SIT, the main signal, is simply equal to all these, and you are able now to recover your 0 zeros. So here you just pick the largest, and it makes sense because only one will be the largest. The others, it's only one whereby the this of the one of this is forms part of this signal, yeah, or this is a product of that particular of the one of this is with the input, yeah. Is that okay? So that is the only one. So you select the largest value. The others will be 0. And that will be the output. So you can see how easy it is to detect signals using the colligation receiver. So long as what was used at the receiver and the transmitter were orthogonal basis functions. So that's what you're seeing there. EI is the energy associated with SIT or the symbol T can be explained in terms of orthogonal components as follows. Yeah, I think this is okay. EI is equal to this. So we are simply saying that the energy you are going to get once you so you detect the energy really. Yeah, so that and we are saying is equal to that. Yeah. It's even shorter than I thought. I thought it would take even an hour. It didn't. Are there any questions? I know we have moved a bit fast because we were trying to beat the time. We didn't have enough time, so we have moved a bit fast and sometimes covering too much in a week. Now we are supposed to have 3 hours, but some weeks we have been covering 6 hours. But I hope we have been able to follow. We have actually finished the syllabus. So when we meet the first week, I think we are going to fully use that first week to just 1 week. We can have maybe 2 double lessons. The one of yesterday, make it double, and like the one of today, so that we don't have to have the one at 4. But those ones we are going to have them physical so that we can go through various examples from various topics, because I have to try to clear the syllabus. We'll give you examples, and examples are very important, especially when it comes to problems that require calculation and all that. So we will look at that in January. So for me, just post your decision on the chat. Yes, Samuel?
Yes, I had a request. Maybe it could be on my end. I don't know.
Yeah.
The request is I wish if we could, or I could get my script, the cut, so that I understand how you mark and I get the feedback.
Okay. Yeah, that's me. Actually, I think I'll do that. I'll send you maybe by the time before you go for Christmas. I have not prepared the marking scheme. I'll just prepare it and post it. I promise this time I think I'll keep my promise. Is that what you're asking for?
Yes, thank you.
Okay, I can do that. Probably I can also give you maybe a past exam with a marking scheme. That could be also help.
Yes.
That could also help. And for me, what I can do for now is to wish you a Merry Christmas, an early, wishing you early Merry Christmas and a Happy New Year, and we will meet next year. I hope it has been exciting. The journey we have had together for the last 11 weeks or so. And of course, we are going to be together for another 12 weeks next semester. So my hope is you have enjoyed this part and you continue. But if you have had issues, of course, you can always either raise them on the classroom, or you can send me SMS, or you can call me, or you can write an email. Don't feel stuck. If you read somewhere in my notes and you do not understand, kindly make a point of calling me. I'll call you back and explain to you whatever you want to know. So again, have a good day, and we see you in January.